We've been learning a lot about how to think about and solve systems of linear equations, and we have seen in some instances the solution set of a system is naturally a geometric object, like a line or a plane, because they are linear combinations of various vectors. So in this lecture, we want to think deeply about the geometry of linear combinations. So let's motivate this with an example. Suppose you have a very restrictive diet and your doctor wants you to consume 100 grams of fat, 130 grams of carbs, and 130 grams of protein every day. But all you have in your house are eggs and oatmeal. A single egg has 5 grams of fat, 1 gram of carbs, and 6 grams of protein in it. A 1/3 cup serving of oatmeal has 1 gram of fat, 9 grams of carbs, and 2 grams of protein. Is it possible to meet your nutritional requirements with just eggs and oatmeal? Notice that this is really a question about vectors, a set of 3 numbers that represent the fat, carb, protein profiles of the foods you eat. And multiplying those vectors by a scalar coefficient corresponds to eating a certain amount of each food, and adding 2 profiles corresponds to eating both foods. So in a 1/3 cup of oatmeal and 2 eggs, you will eat 1, 9, 2 plus 2 times 5, 1, 6, and that equals 11, 14 grams of fat, carbs, and protein. Thus, if my doctor says I need to consume a certain nutrition profile of 100, 130, 130, then the question I'm asking is this. Is 100, 130, 130 a linear combination of 516 and 192? In other words, is it a linear combination of eggs and oatmeal? And actually, we hope to know something more. We want it to be a non-negative linear combination because you can't consume a negative amount of food. So recall from an earlier lecture that the span of a set of vectors is the set of all linear combinations of those vectors. If you have just one vector in Rn, the set of all linear combinations of that one vector is just multiples of that vector. This forms a set that's just a line in Rn. So for instance, the vector 2, 1 lives in the plane. Then the span of the vector 2, 1 is anything of the form given by some constant k times 2, 1. So anything of the form 2k, k is in the span of 2, 1. Note that k could be negative. So this forms a line in the plane because you can go both forwards and backwards in the direction of 2, 1. The span of 2 vectors, say v1 and v2, is the set of all linear combinations of v1 and v2. This means it could be any multiple of v1 plus any multiple of v2. And another way to say it is the span of a set of vectors is the set of all points you could reach from the origin if you were limited to adding multiples of these 2 vectors. So consider 2 vectors v1 and v2 sitting in 3-dimensional space, as in this picture, where v1 and v2 are based at a blue dot, which represents the origin. If I just draw integer multiples of v1 plus integer multiples of v2, you will get the set of points of a grid, as in this picture. So this is the point representing v1 plus v2, because you can get here by marching first in the direction v1 and then v2. And this is the point v1 minus v2, because you can get here by first moving in the direction v1 and then in the direction of minus v2, which is the opposite of the direction v2. And over here is 2 times v1 plus v2. How do you get from the blue point to the point B using v1 and v2? Take a moment to think about this, perhaps by pausing the video. A moment's thought will show that you can use 2 multiples of v2 plus 1/2 of v1. Now here's another question. Is there another linear combination of v1 and v2 that will produce the vector b? I'll let you think about that. Now hopefully thinking about this figure helps you think about what happens in 3 dimensions. If you have 2 vectors, v1 and v2, any linear combination of v1 and v2 will produce a point on a plane containing v1 and v2. And those are intuitively the only points I could reach. So you can see with just 2 vectors, I won't be able to reach every point in R3. So the span of 2 vectors is a plane. The span of any 2 vectors is generally a plane, but if v1 and v2 are parallel, pointing in the same or perhaps opposite directions, their span would just be a line. And if v1 and v2 are the 0 vector, then the span of v1 and v2 will just be a single point, the 0 vector, since that's all you can get by taking linear combinations of the 0 vector. Similarly, the span of 3 vectors can be something at most 3-dimensional, and the span of k vectors can be at most k-dimensional in some high-dimensional space, but it could also be smaller. Now, this kind of stuff may seem abstract, but the intuition can be very useful, as we shall see. Let's look at a couple of examples. Suppose I ask you to find the span of the vectors 1, 0 and 0, 1. The first thing you might do is think about this intuitively. Let me roughly indicate this with my hands. 1, 0 and 0, 1 are 2-dimensional vectors, so they live in R2. And there are 2 of them, which means they span at most a plane, but if we were unlucky, they might have spanned something smaller if they were different vectors. Since they span a plane, there's only one plane they could span, namely all of R2. So let us think about this. Can you get any vector AB as a linear combination of 1, 0 and 0, 1? Well, sure you can. This is just what you do with the usual coordinate system. You march over A units in the x direction and B units in the y direction. And this is just doing the combination A times 1, 0 plus B times 0, 1. So the span of these 2 vectors is all of R2. On the other hand, the span of the vectors 1, 0 and 2, 0 is just a line consisting of all points of the form x, 0 for a real number x. You can see this in the case that taking linear combinations of 1, 0 and 2, 0 will only produce vectors whose second coordinate is 0. All right, what about the span of the vectors 1, 3 and 3, 1? Again, the vectors are in the plane R2 and they should span at most a plane. We expect that as long as they don't point in the same direction, they should span the whole plane. Now, it may not be as obvious how to construct an arbitrary vector AB as a combination of 1, 3 and 3, 1. So let's figure out how to do that. The general question before us is, when is a vector B in the span of a set of vectors v1 through vk? In other words, when is B a linear combination of given vectors, and if it is, what linear combination is it? For instance, is 1, 2, 3 in the span of the 2 vectors 4, 5, 6 and 7, 8, 9? Asking this question is the same as finding coefficients x1 and x2 to make x1 times 4, 5, 6 plus x2 times 7, 8, 9 equal to 1, 2, 3. But notice that this is just a linear system of equations. You see, for instance, that the first row is 4x1 plus 7x2 equals 1, and the other rows are similarly linear equations. So finding coefficients x1 and x2 is the same as taking the augmented matrix and reducing it by row operations. And when you put it in reduced row echelon form, you see that there is no inconsistency because there is no row that is all zeros on the left while being non-zero on the right. This RREF shows that a solution exists, namely x1 equals 2 and x2 equals -1. So the answer to our question is yes. 1, 2, 3 is in the span of the two vectors, and we just solved for the coefficients. So we know that 1, 2, 3 is 2 times 4, 5, 6 plus -1 times 7, 8, 9. In fact, we know this is the only linear combination that would produce 1, 2, 3 because it was the only solution to the system of linear equations that we had. So, if 4, 5, 6, and 7, 8, 9 were nutrition profiles of two foods, I would not be able to eat a combination of foods to produce a nutrition profile of 1, 2, 3, because the only combination that produces 1, 2, 3 has a negative second coefficient. Now let me draw your attention to the RREF of the augmented matrix. Remember, RREF means reduced row echelon form. The last row here is a row of zeros. And you could have foreseen that there would be a row of zeros on the left side because there are more rows than columns on the left side, which comes from the fact that the dimension of the vectors, which is 3, is greater than the number of vectors that we are taking the span of, in this case, 2 vectors. However, on the right, the last row may not have had a 0 if we had row reduced a different vector besides 1, 2, 3. So we could have had an inconsistency, which suggests that not all vectors in R3 are in the span of 4, 5, 6, and 7, 8, 9. And this makes sense, because the span of two vectors is at most a plane in R3. All right, let's summarize what we've learned in the following theorem. The system of equations ax equals b has a solution if and only if b is a linear combination of the columns of A. Or, said another way, ax equals b has a solution if and only if b is in the span of the columns of A. And this is an answer to our question, how do we tell when a vector is in the span of a set of vectors? Just solve a certain matrix equation. This is a good time to point out that we've been moving back and forth between what appear to be 3 different things but are really the same things. A matrix equation, a system of equations, and a vector equation. Look at this example and notice how they are all saying the same thing. At one corner of this triangle, we have a matrix equation of the form ax equals b. And if you write out what it is saying, you will get the system of linear equations that's in the bottom left corner. But if you look at this system of equations and pull out the dependence on x1, x2, and x3 as coefficients of vectors which are the columns of A, then you get the vector equation in the bottom right corner, which asks what linear combination of these columns equals the vector b. Since we will see and use this correspondence a lot, we'll refer to it as the fundamental correspondence between a matrix equation, a vector equation, and a system of equations. And it's worth staring at this correspondence for a little while. Each of these corners of the triangle is saying exactly the same thing. We have seen that if you have fewer vectors than dimensions, you might not span the entire space. What if you have more vectors than dimensions? Suppose we have 3 vectors in R2. Let's say the vector u is 1, 0, the vector v is 0, 1, and the vector w is 2, 3. What do they span? I'll give you a moment to think about this. Well, we have already seen that 1, 0, and 0, 1 span all of R2. So we expect that if we throw in another vector, the span should only get bigger. But it can't get bigger because we've already spanned the entire space, R2. So our intuition is a good guide here. But now let's see what insights the fundamental correspondence might tell us. The fundamental correspondence suggests that finding the span of these three vectors is the same as seeing if a certain system of equations has a solution, the one represented by this augmented matrix. Notice how the columns on the left are the vectors u, v, and w that I was given, and the right side is a generic point B with coordinates b1 and b2. By putting generic letters for b1 and b2, I am asking for which b1 and b2 is a solution possible. In other words, which vectors b are in the span of these three vectors. Solving this particular augmented matrix is easy because it's already in RREF. So it represents the system x1 plus 2x3 equals b1 and x2 plus 3x3 equals b2. Recall the variables x1 and x2 and x3 will tell me the linear combination of the columns that produce the vector b1, b2. Also, we see from the RREF that x1 and x2 are leading variables associated with the leading ones, and x3 is a free variable because the column for x3 has no leading one in it. So to solve this system, I should try to express all the variables in terms of the free variable. And when I do that, I see that x1 equals b1 minus 2x3, and x2 equals b2 minus 3x3. And x3 is free, so it's easily expressed in terms of x3 just by adding the equation x3 equals x3. So we get this vector equation. x1, x2, x3 equals b1, b2, 0 plus x3 times the vector minus 2, minus 3, 1. These are the coefficients of the combinations that will produce the vector b1, b2 from the three vectors u, v, and w. This solution should not surprise us, because if x3 is 0, we get the result we got before, that every vector b1, b2 can be produced as a linear combination of 1, 0, and 0, 1, with coefficients that are just the coordinates b1 and b2. So if you want to get the point 5, 7, you just use 5 times 1, 0 and 7 times 0, 1. We knew this already. But what I want you to notice from this analysis now is that we see there are actually multiple solutions. In fact, a whole line of solutions. Each solution given by a different choice of the free variable x3. So if I want to get 5, 7 using 1 as a coefficient for the vector w, then I'll need x3 equal to 1. So then, x1, x2, x3 equals 5, 7, 0 plus 1 times minus 2 minus 3, 1 equals 3, 4, 1. Going back to the vectors u, v, and w, this means 3 times 1, 0 plus 4 times 0, 1 plus 1 times 2, 3 equals 5, 7. Thus, the linear combination you get to produce a particular vector in this case is not unique. This was because we had the presence of a free variable, in this case x3. And we had that free variable because we had more vectors than dimensions. Now, to be clear, it is possible in a case like this that the RREF could reveal an inconsistency. For instance, a set of 3 vectors might still span a line in R2, and not every point in R2 is a linear combination of those 3 vectors. But if there is no inconsistency and you have more vectors than dimensions, then linear combinations that produce a specific vector are not unique. Another way to look at it is, when you have more vectors than dimensions, you don't need all the vectors to produce the span of those vectors. Some of the vectors are redundant for that purpose. In our example, we didn't need the vector 2, 3. I could have thrown it out and the other two vectors would still produce all of R2. In fact, W equals 2, 3 is a linear combination of the other two vectors. It's just 2u plus 3v. So anything I could form using 2, 3 could also be formed using 1, 0 and 0, 1. And that's one sense in which the vector 2, 3 is redundant. This leads us to an important concept that describes when a set of vectors is redundant in that sense. We call it linear dependence. Now, the definition I'm about to make may not seem at first that it's related, but you'll soon see why it is. We're going to say a set of vectors is linearly dependent if there are coefficients, we call them weights, not all 0, such that a linear combination of those vectors equals a 0 vector. Otherwise, we say the set of vectors is linearly independent. Notice in this definition, I'm not requiring all coefficients to be non-zero, just some of them. We call this situation a non-trivial linear combination when some of the coefficients are non-zero. If they were all 0, we'd call it the trivial linear combination. Let's look at our earlier example with u, v, and w. We've already seen w is a linear combination of u and v already, namely w equals 2u plus 3v. Now, do you see that this is saying the same thing as 2u plus 3v minus w equals a 0 vector? In other words, if one vector can be written in terms of the others, then there is a non-trivial linear combination that produces the 0 vector. And if there is a non-trivial linear combination, by solving for one of the vectors in terms of the others, we'd see that one of the vectors is a linear combination of the others. So we've just proved a theorem that the set of vectors is linearly dependent if and only if at least one vector is a linear combination of the others. So the vector that is a linear combination of the others could be removed from the set of vectors and you would not change its span. We would have just removed a redundant vector. Note that when you have a linearly dependent set, we're not saying that every vector is a linear combination of the others, just that one of the vectors, at least one of the vectors, is a linear combination of the others. For instance, if you have vectors a, b, and c, and vectors a and c are multiples of one another, while b points in a different direction, then you wouldn't be able to remove b without changing the span, and b is not a linear combination of the vectors a and c. And that's because the non-trivial combination of a, b, and c that produces a 0 vector is a minus 2c equals 0. The coefficient b in this non-trivial linear combination is 0, so this linear dependency relationship does not involve b. I'd like you to also notice a language we use. Linear dependence or independence is a property of a set of vectors. It's not a property of a single vector. And a common mistake people make is to talk about a single vector as dependent or independent. But that has no meaning apart from a set that you are speaking about. All right, let's now connect our discussion of linear independence of a set of vectors to the uniqueness of a linear combination of those vectors. A set of vectors is linearly independent means that the only way to get to the 0 vector as a linear combination is if the coefficients are all 0. This is equivalent to saying that the 0 vector is in the span of a set of vectors in exactly one way. By the fundamental correspondence between vector equations and linear equations, this is just a statement about a system of linear equations. If you put a set of vectors in the columns of a matrix A, then to say the columns are linearly independent means the only way to get the 0 vector as a linear combination of the columns is if all coefficients are 0. In other words, ax equals 0 has only the trivial solution, where all coefficients are 0. And we can see from the RREF of A that you have linear independence of the columns if there are no free variables in the RREF. By the way, a system of equations of the form ax equals 0 has a special name. It's called a homogeneous system of equations. And notice that it can always be solved because a times the 0 vector gives the 0 vector. So the 0 vector is always a solution of a homogeneous system, and it's called the trivial solution. So a homogeneous system of equations can never have an inconsistency. So the only question for a homogeneous system is whether the trivial solution is the unique solution. Otherwise, ax equals 0 has more than one solution, which happens when there are free variables in the reduced row echelon form. Let's take a look at these matrices. Take a moment to think about whether the columns are linearly dependent. You might pause the video to think about it. For the matrix A, you can see that it is already in REF. And the form shows that every column has a leading entry. So the associated system of linear equations, ax equals 0, has no free variables. So the columns are linearly independent. For the matrix B, if you notice that the second column is a multiple of the first, in fact, -3 times the first, then the columns cannot be linearly independent. Another way to say this is 3 times the first column plus 1 times the second column equals the 0 vector. Still another way to say this is the matrix B times the vector 3, 1 gives the 0 vector. And if you take a look at these two equations together, you will see that it's a fundamental example of the fundamental correspondence between a matrix equation and a vector equation. So let's return to our questionnaire that we started our lecture with. My doctor has told me to eat 100, 130, 130 grams of fat, carbs, and protein a day, and I only have eggs and oatmeal. Can I do it? We've seen that this is equivalent to asking whether the vector 100, 130, 130 is in the span of the vector 516, the nutrition profile of an egg, and the vector 192, the nutrition profile of a third cup of oatmeal. So I want to know if I can solve a system represented by an augmented matrix like this, with columns 516 and 192, and on the right side, the column 100, 130, 130. If we row reduce, we obtain this, from which we conclude, since the system is consistent, that indeed eggs and oatmeal are enough to get my nutritional demands met. And we see x1 equals 17.5 and x2 equals 12.5. So I know that 17.5 eggs and 12.5 servings of oatmeal, each 1/3 cup, will do it. But beyond solving this specific problem algebraically, notice what we have also learned from developing our geometric thinking in this lecture. I realize that not every nutritional profile my doctor could have asked of me is possible from eggs and oatmeal, because the set of profiles is three-dimensional, with axes of fat, carbs, and protein. But I only have 2 food types. And the 2 food types can't span all of these 3 dimensions. So we were very lucky. A profile that could be met by these 2 foods was the one that we were given. Almost any other profile you might try won't be possible to achieve with just 2 foods. Just pick one and see for yourself. I also realized that if I wanted to be sure I could get my needs met for any nutritional profile, that I would need at least 3 foods. And those foods would have to be linearly independent nutrition profiles, otherwise one of the foods could be removed without changing the span of the other 2 foods, and then I'd only be able to span 2 dimensions in that case. But if I had 3 linearly independent nutrition profiles, then my nutritional demands could be met in exactly one way. And if that linear combination of foods happens to have some negative coefficients, then it won't be possible to meet my nutritional demands with those 3 foods unless I throw up food. So then I may need more than 3 foods to achieve a positive linear combination. So if I want to have the liberty of variety and not be bored with what I'm eating every day, I would probably want 4 or more foods in my pantry that span these 3 dimensions so that I have a linearly dependent set of foods. And if I wanted to consume a specified amount, not only of fat, carbs, and protein, but also more things like sodium and vitamin D, then that would be a 5-dimensional space in nutritional profiles. And even if I can't visualize 5 dimensions, the intuition we are building here helps us see that what I would need is at least 5 foods to span this space and at least 6 foods if I wanted to have variety in my diet. So we see how geometric thinking and algebraic thinking can go hand in hand to give us a deeper insight into structure that was hidden before. And the ideas we developed here will lead to a more precise notion of the word dimension and what it really means in a future lecture.